Okay. Good morning, afternoon. Actually, most likely it's afternoon by everybody's place. And welcome to the demo day of the QTEdu community. We are happy to host today Laurent Prost from Alice&Bob, and he will be presenting us Felix. And this is their creation, the creation of Alice&Bob, the first quantum emulator of its kind. So we are looking forward for the presentation of Laurent. And after that, there will be about half an hour for questions and answers. Welcome, Laurent.
Okay. Hi, Oksana. Thank you for having me today. And yes, we will be talking today about Felis, which is Alice&Bob toolkit to play with cat qubits, and more specifically to work with physical and logical cat qubits. So I will have a few slides in order to give you a quick introduction to what we do at Alice&Bob, but then I will want to spend most of my time showing you actual code that is running, and we'll talk about error correction, about how to build logical qubits and how to use them using live examples. And then, of course, you will have all the links to retrieve what we did today and to go further on your own if you are interested, of course, in learning more, because just an hour is, of course, not enough to cover everything that there is to say on this topic. I'm going to share my screen so you can see the presentation.
It's already there.
So it's already there. Okay, because okay, I usually have a frame, but it was no longer showing. But okay, so we're already in the presentation. Good. All right. So yeah, before we start, a few words of introduction. A few words of introduction about myself. So Laurent Prost, I'm product manager at Alice&Bob. I'm working on making our quantum computers available over the cloud. And so I'm working for Alice&Bob, a French startup focused on building a fault-tolerant quantum computer based on cat qubits. We're going to explain what this is right after. But we have been founded in 2020, 5 years ago. We are now over 120 people spread over 2 offices. So most of the people are in Paris, but we also recently opened an office with a couple of people in Boston to work with both public and private institutions in the United States. And we've raised 130 million euros to date with the latest fundraising dating back to December 2024, where we raised 100 million euros that will enable us to scale our operations with a new site that will be opening in the Paris region very soon, enabling us to work on building our own chips and then having more room, of course, to experiment with different chips in order to accelerate what we do and the advent, of course, of a fault-tolerant quantum computer. And I want to say a few words about what it takes to actually build a fault-tolerant quantum computer, because right now this is still a challenge. This is still something for which we need to find better solutions. And one of the biggest issues we have when we try to build a fault-tolerant quantum computer, of course, is that implementing error correction adds a big overhead to the number of qubits that you're going to need. And so if you're starting from one noisy physical qubit using standard approaches like transplant qubits with a surface code, then you need to have about 1,000 of these qubits in order to have a logical qubit with extremely low error rate. Here we're using the kind of error rate you need to decrypt RSA 2048, which is about 10 to the minus 15. But yeah, so for every single physical qubit you need, for every single perfect qubit you need to have about 1,000 physical qubits. And that is a problem, of course, because if you want to have just a single physical qubit in terms of cost and power consumption, you're talking about something like $10 million for about 50 kilowatts of power. But then you only have a single logical qubit, and you're not doing much with that. So if you want to start to have a machine that is interesting, then you might want to go to 100 logical qubits. But then the cost of the machine starts to reach about $1 billion. Power consumption is about 500 kilowatts. So this is starting to be serious with 100,000 physical qubits. And here, if you want to have something that is that big, then you have something that is basically the size of a regular data center on its own. So you're not even talking about integrating this in an existing data center. You're talking about building something uh, that's just a self-standing facility. And then even 100 logical qubits is still not enough to run Shor's algorithm on a big number, and so realize the promises of quantum computing for cryptography. And if you want to do that, then you would rather need something like 20,000 logical qubits, translating into 20 million physical qubits. And here we're talking about a big stack of data centers, as you can see, so higher than the Eiffel Tower. And we're talking about hundreds of billions and hundreds of megawatts of power. So, needless to say that this is not a viable route to filter on quantum computer. This is likely not what it will look like eventually. And so we need to find better solutions for that. And the solution that we're betting on at Alice&Bob is cat qubits. The reason why we like cat qubits so much is that there are a specific type of qubit, so the specific type of superconducting qubit that can be tuned to remove bit flip errors almost entirely by design from the qubit, meaning that error correction then becomes much more simple because you only have one dimension of error to correct rather than two. And you will see this right after when we dive into the actual code. You will see that we're able to work with error correction codes that are much simpler than if you have to correct for the two dimensions at the same time. We're currently working in our lab with a 16 cat qubit chip that should enable us to prove a first logical qubit and also prove that the error rates of the logical qubit are decreasing exponentially with the time with the number of qubits that you involve. So we should be able to reproduce distance 3, 5, and 7 with 16 cat qubits, and so start to draw the exponential curve that shows that you're actually able to correct errors. But if we take a step back and look at where we are going, then basically the 20 million estimate goes back to a scale down to 100,000 qubits in order to run Shor's algorithm on the 2000-bit number using cat qubits. So that's a 200 times reduction in the number of qubits that you need, and it makes quantum computing much more practical. Now, of course, you're going to say 100,000 qubits is still a lot. It's still the size of a regular data center, and I agree with you, which is why by 2030, we have a first milestone with 100 logical qubits that would be implemented with 2,000 physical cat qubits, and that we think can fit in a single cryostat, the kind of which we are already using today. And so in order to get there will be several steps, of course. The first step is to demonstrate the properties of cat qubits, and in particular, the resistance to bit flips. So in order to do that, we've released the Boson 4 chip on the Google Cloud Marketplace, and I'm going to demonstrate it to you right after we finish these slides. You will see it working live. Then internally, so we are working on building the first logical qubit, so on assembling several qubits like Boson 4 to make them work together to detect and correct errors. So this is what we're doing currently. And then the next steps on the way to the 100 logical qubits will be, first of all, to realize a long-lived logical qubit and first logical operations between logical qubits. So this is going to be the lithium chip, which is going to demonstrate a first logical CNOT gate. But at this point, lithium will not be enough to demonstrate a universal set of gates where you can run virtually any quantum program that you like. And this is going to be the next step. This is going to be beryllium, which is going to feature 250 cat qubits for 5 logical qubits. And there you will be able to run virtually any quantum program with 5 qubits that you like, with a 10 to the minus 4, logical error rate. And with that, we will land in 2030 with the first useful fault-tolerant quantum computer featuring 100 logical qubits at a 10 to the minus 6 error rate. And also, of course, with a 1 microsecond clock speed, because we're using superconducting, so we're also benefiting from the speed of superconducting circuits in comparison with other technologies. And what I want to show you today is Felis, so the software toolbox that we've developed for cat qubits. And so it has different use cases. So first of all, you can work with actual physical CAD qubits to benchmark, so the boson for chip that we've put on the cloud, and also work with emulators for producing the behavior of CAD qubits to do error correction experiments. So we're going to show that right after. Then we also have a logical qubit emulator in Felis, which enables you to reproduce the behavior of logical qubits when all error correction will be implemented and we can start to forget about it. So you will see what the experience looks like. And then we have also a resource estimator, which enables you to predict how many qubits you're going to need in order to run a specific program that you're interested in. So how many physical qubits, of course, starting from a program that you designed with logical qubits in mind. So this is an overview of what we'll be seeing today. We'll focus more specifically on the physical and logical qubit emulators. The resource estimator will unfortunately not have the time to go through it, but you have the links here and you will be able to explore that on your own if you like. So we're going to share the screen again because it looks like we've lost it. And we're going to switch to the demo. Can now everyone see my screen? And there should be code on the screen.
Yes, we see the code. Just that, if possible, to enlarge a little bit because the code is very small.
Okay, yeah, sure. Okay, is it better this way?
Another couple of times, and then.
Okay, like so?
Yeah, I think like this it's readable.
Is it more readable for everyone?
I think a couple of more would be even better.
Okay, right. Then like this. Okay, maybe before we go and dive into the code, does anyone have any questions while we're at it? Just to clarify what we just said. No.
Let's see if there are. Please write questions in the chat or raise your hand.
Okay, all good. All good for now, it seems.
All good for now.
Okay, good. All right. So I want to show you how we can build and work with logical qubits. And to do that, I'm going to be using both Felis and Qiskit because Felis is actually built on top of Qiskit. It uses Qiskit circuits. Felis is basically a way to provide you with backends for producing the behavior of CAD qubits, but these are basically Qiskit backends. So we'll be working with Qiskit circuits a lot, as you will see, and then we will add Felis when we need to reproduce the specific behavior of CAD qubits for the circuits that we're studying. And I'm going to start. I trust that everybody here has already a little experience with Qiskit, but if you don't, then very quickly. So I'm going to start with a very simple circuit where we are initializing the qubit in the zero state. We're applying an X gate, and then we're measuring the result. Of course, you would expect this circuit to yield 1 as a result when you execute it. And as you can see it, of course, when I execute it 1,000 times and I get 1,000 times 1, because here I'm using a noiseless simulator. This is at least the theory. This is how you would like quantum computers to work, okay? You have a circuit that's supposed to get 1, you're expecting to get 1 eventually. But if you try to use real hardware, then it's usually not so simple. Because here I'm going to be using a fake IBM backend. So I'm going to be using the Fez computer, which is based on a Heron R2 processor. So the latest and best computer that IBM has to offer right now. And I'm using the fake provider because, especially for the demo, it makes it's going to be running and I will not be stuck in a queue behind I don't know how many users who are trying to run actual jobs and not just simple tests like the one that I'm doing here. And so as you can see, when I'm running on the simulator, reproducing the behavior of the actual computer, when I'm running the same circuit, then of course I'm getting a lot of ones, 98.4% of ones, but I'm also getting 1.6% of zeros. And I did nothing but ask a state to be prepared and then to be read. And as you can imagine, I mean, just think about it in a classical computing from a classical computing perspective. How happy would you be if you would just try to store a single bit, and then when you try to read it, there's a 2% error rate? That's a bit annoying, right? But that's not all there is, because here I just read the result immediately. But if I try to just introduce a small waiting time, here I'm introducing a 1 millisecond wait. Okay, so this is very short, shorter than the blink of an eye. And I'm running the circuit again. So here I'm still targeting the same backend as before. I'm still targeting the IBM Fez machine with the Heron R2 processor. This is by the way, this is a 156 qubit chip. Of course, I don't expect that it reproduces all of this at the same time, but here we're using a single qubit, so we don't care. And as you can see here, after just 1 millisecond, we've basically lost our state. Here, all the measurements yield 0. Nearly all of them, there's only 2 out of 1,000 that are yielding, they're still yielding 1, which is what we wanted to have here. So I hope I don't need to convince you, and if you've already worked with your hardware, I guess you've already witnessed this, that, yeah, basically running long programs is not for this kind of machines. But now we'll look at how a cat qubit behaves in the same setting. And here I will be connecting directly to Boson 4, our cat qubit chip that is available over the cloud. And I will be sending the same circuit as before, but to run on the actual chip. And so here, as you can see, it's running, it's been compiled, executed. And how many errors are we going to get? This is running on real hardware. So that is stored in that is running in our Paris office right now. Okay, it sometimes takes a little bit longer because here this execution, because we're doing 1,000 repetitions of a 1 millisecond wait time, sometimes it takes a bit longer because the chip is constantly testing itself. And I think that here we were just waiting behind an auto test. But here, as you can see, the execution is complete. We've spent 1.63 seconds on the QPU, and we have 1,000 times 1 out of 1,000 trials, as we would expect. So what you see here is the exceptional resistance of cat qubits to bit flip errors. Unfortunately, we don't have time for live demo today to show you the full extent of what we can do with these experiments. But if you have time and if you wanna go to the Google Cloud Marketplace to test Boson 4 for yourself, there is a free hour of experiments that you can use, and you can try to reproduce then at least a part of the curve that we can see here. So I'm going to zoom out a little bit so we can see it in full. And here, what you can see is that when you can tune a cat qubit with a number of photons that you have here. Okay, so this is a number of photons, and you can tune the cat qubit to enhance its resistance to bit flips. And so when you're working with a low number of photons, then you have short lifetimes of about 1 millisecond. And then when you have a high number of photons, then you have a very long lifetime. And as you can see, when we're working with 12 photons, we're saturating at 430 seconds. That's about 7 minutes of bit chip lifetime. Above, to be complete, I was using, as you can see, 11 photons. And so here, when we're at 11 photons, we're at something like 2 minutes of lifetime. And of course, when we do a 1 millisecond experiment, the probability of experiencing a bit flip is extremely low. Now, unfortunately, there is no, sorry. So you can reproduce this by going to the Google Cloud Marketplace and then by using the notebook that I have shared in the link here, and we'll go back to this later also. Now, unfortunately, of course, there is no free lunch. And so the exceptional stability that we have on the bit flip side is paid with a lower stability on the phase flip side. And we can see that if we prepare so a specific circuit in order to measure phase flips this time. And so here, what I'm doing is I'm preparing the plus state and then measuring in the X basis. So these two instructions here, as you see, are not native Qiskit instructions, sorry. So they are specific to cat qubits, and for this, we need to run through Felis. And this is why here I'm going to get as a backend still boson 4, so a specific Alice&Bob backend in order to run this. And I'm going to be running on a real chip again. And the circuit is being executed. And here this is shorter. And as you can see, we would expect, if there were no noise, to have 1,000 times 0, because this is the code for plus. We would expect to have 1,000 times 0, and here we're only getting 64% of 0. So obviously the performance on the phase shift front is not as good as the performance on the BFG side. But the good thing is that all the errors that we're experiencing are focused on one single dimension. And what it means is that we'll be able to use much simpler error correction codes. And we're going to do that. So if you've never designed error correction circuits, then you will see how this works. And I'm going to start showing you how it works with bit flips, because with phase flips it's slightly more complicated. It's a bit easier to explain with bit flips, and we're going to do the phase flips right after. So here with bitflip, so what I'm doing is I'm using 3 qubits. 2 qubits are going to be carrying my data, so Q0 and Q2. And Q1 is going to be an ancilla qubit that we'll use for measurements, and that is basically surveying whether these 2 qubits are in agreement. Because we have 2 CNOT gates here, what happens is that if these 2 qubits are both at 0, then basically nothing is going to happen on the ancilla, and I'm going to read 0. If these 2 qubits are in the one state at the same time, then basically the ancilla will flip 2 times and will also read 0. But if these two are not in the same state, if one is at 1 and the other is at 0, then the ancilla is going to be flipped once, but not a second time, and then we'll read 1 and we'll detect an error. So we can check that when we do this, we can check that when we do this, then we actually measure 0 1,000 times, because we're here. I'm going back to the noiseless simulator. Okay. And so I'm not detecting any error because I didn't introduce any. I don't have errors in my backend. I don't have errors in my circuit. But if you want to see what it looks like when we do have an error, then I'm using here the same circuit. I'm just adding an X gate on the first qubit in order to introduce the equivalent of an error. And when I run my circuit, then as you can see, I'm getting 1 1,000 times, of course, because it detected an error. So when the ancilla qubit that you have here measures to 1, then it means you detected an error. And otherwise, you just read 0. The problem is, of course, with what we have above here is that, okay, we know that there is an error because the ancilla measured 1, but we do not know whether the error happened on the first or the second qubit. Here, of course, I know because I introduced the error myself, but in real life, of course, you don't know where the errors are coming from. You only witness that there was a measurement that told you there was an error. So if you want to detect where the error was, then you need to have more qubits. And here we'll be working with 5 qubits. So 3 qubits to carry your data and 2 qubits as ancillas. And we'll be doing the measurements on the ancillas here. And so this ancilla is going basically to tell you whether these two are in agreement. And this ancilla is going to tell you whether these two are in agreement. And when we run the circuit, as expected, of course, because there is no error again, we measure 0, 0, because there is no error in the model, there is no error in the backend. And of course, we can check that errors are correctly detected if we do add an error to the circuit. So I'm using, again, the same circuit as before, adding an error on the first qubit. And when I run this, you can see that here, this time I'm measuring 0, 1. So Qiskit names the classical bits from right to left. So 1 is the measurement of the first ancilla, so this is the measurement of this one, and 0 is the measurement of this one. And you can see that, as expected, this one detected an error between these two and detected that these two are not in agreement. And this one said that these two are actually in agreement. So if we decode this, if we analyze the result of this, what we call syndromes here, we can know that the error happened on the first qubit just by reading the results of the measurements and knowing nothing about the circuit that actually generated the error. So now you've seen the basics of error correction. So how can you detect errors and know where they happened? But of course, now we want this to work on phase flips and not on bit flips because the protection of cat qubits is against bit flips. So in order to do this, it's actually quite easy because we can witness that there is a specific property to a CNOT gate, which is that when you're working in a computational basis, the CNOT gate uses the first qubit and flips the result of the second qubit based on the value of the first one. So if the value of the first one, the control qubit is 1, then the other is flipped. And as you can see here, 1, 0 becomes 1, 1, and 1, 1 becomes 1, 0. But when you're working in the Hadamard basis, so plus and minus, it actually works in reverse. So this time it's the target qubit that is acting on the control qubit. And as you can see here, when the target qubit is in the minus state, then the control qubit gets flipped. And when the target qubit is in the plus state, then nothing happens on the control qubit. So what we need to do in order to detect phase flips is we just need to reverse the CNOT gates. And this gives us a circuit like that when we're just doing error detection with 3 qubits. As you can see now, the targets are on the data qubits and no longer on the ancilla qubits. And of course, we can verify that this detects no error as expected. Here, as you can see, we have 0 as we would expect because 0 is the code for plus when we are in the Hadamard basis. You can see here also that we're using H gates in order to go in the Hadamard base and in order to read the Hadamard base in the Hadamard base. This is because I'm using the AER simulator here that is provided by Qiskit. But when you're working with Felis, then you can use native instructions to prepare and read in the Hadamard basis. And this is what I'm going to do right after. Sorry, maybe just after I check that we can actually detect an error. In this case, we're detecting Z errors. So I'm adding a Z gate to my circuit. And as you can see, now my ancilla detects 1, which is what I expected. Okay, so yes, we are now going to create a logical qubit with phase flip error correction. So here with 3 data qubits and 2 ancilla qubits to measure them. So this is the same principle as before, but this time targeting phase flips. So you notice that when I'm looking at my ancilla qubits, then I do have my controls are on the ancilla and my target is on my data. And when I run this, then I can, of course, check that here my measurements are 0, 0 because we're still in not noisy situation. But when we do add noise and when we use Felis in order to do that, so first of all, we're going to use a slightly different circuit because Felis recognizes the preparation and the measurement directly in the X basis. And this is not just for convenience. It's also because at the physical level, when you're working with physical cat qubits like this, you do not want to use Hadamard gate. The problem we have with Hadamard gate is that they are going to transform phase flip errors into bit flip errors. And we do not want this to happen because we want to preserve the noise bias that we have in cat qubits. We do not want to mix the 2 channels of error. And so this is why it's important to have native operations that will work directly in the Hadamard basis without the need to use Hadamard gate. And one consequence of that, if you also paid attention, is that you will not be able to use physical cat qubits in order to run algorithms like you are probably used to running, because you will not be able at the physical level to use Hadamard gate to create the superpositions that you need in most quantum algorithms and then also to manipulate information. If you want to use Hadamard gates, of course it's possible, but it's possible at the logical level after applying error correction and not directly at the physical level. So here we have a circuit that is preparing plus states and that is then applying measure X on the results. So the more native implementation than the one with Hadamard gates we had before. And I'm going to be running here on the backend that is featuring 6 physical cat qubits, and for which I set 2 parameters. So there is the average number of photons. So this is the what you saw earlier, the parameter that you can tune in order to adjust the bit flip lifetime. But you need to know that it also affects the phase flip lifetime. So we have an exponential increase of the bit flip lifetime as we increase the number of photons, but we also have a linear decrease of the phase flip lifetime as we increase the number of photons. So you can witness that by playing with average number of photons. And then you have kappa 1 and kappa 2, which are two quality factors of the cat qubits. You want kappa 1 to be as small as possible, and you want kappa 2 to be as large as possible. Kappa 2 is basically the stabilization mechanism of the qubit that enables you to have these very long bit flip lifetimes. And kappa 1 is the rate at which you're going to lose photons in the cat qubit, and of course, you want that to be as small as possible. And as you can see, when we're running that through a noisy backend, then we're starting to get results that are, again, unexpected because we would expect to see 0, 0. But when we do have errors, then we are measuring 0, 1, 1, 0, 1, 1, etc. And so you can use that as a basis to do your error correction experiment. You can use that as a way to generate errors and then measure to what extent you are able to spot them and correct them with the full noise model of cat qubits. We will not be doing this today. There are some samples in our sample repo that will show and that enable you to do this. But before we move, instead of diving into the error models with which you can experiment, I want to talk about logical gates. And in particular, because, okay, creating a logical qubit is great, but it's only about storing information. It's not about actually using it. And what you want to do, of course, in quantum computing is manipulate information and do operations on logical qubits and between logical qubits. And for some operations, it's going to be simple. So if we want to apply a logical Z gate to our qubits, then this is basically going to work this way. So we're going to add just Z gates to the data qubits, not to the NCLS, only to the data qubits. And when we run the circuit, you will see that the results that we're getting is 1, 0, 1, 0, 1. And as expected, we have flipped all our data qubits, and our ancilla qubits are still measuring 0. They're still measuring that the qubits are in agreement. So we've successfully moved the logical qubit from the 0 state to the 1 state. Okay, this is how it should work. Again, in a noiseless setting, which is what I'm using here, which is also where you see the Hadamard gates again. But then, of course, when there are actual errors, then this enables you to spot them and to correct them. But yeah, so we've been able to apply a Z gate here, and we've done that in what we call a transversal manner, which is that we've basically took the gate that we wanted to apply and we applied it to all the physical qubits. But unfortunately, that doesn't work for all the gates. And in particular, there is a gate that causes trouble, which is the T gate. And here I'm going to use exactly the same construction as before. So the T gate here is it's a phase gate that adds e to the I pi over 4 a factor to the one state when you apply it and leaves the 0 untouched. And here you see I'm using exactly the same construction as for the Z gate, but I'm using T gates instead. And when I do run the T gate, then as you can see, this becomes a big mess. It becomes a big mess because here we have states that we are not expecting to see in a noiseless setting. You understand that because the logical qubit is representing a superposition of logical 0 and logical 1 states, the logical 1 state is the one that we had here. You see, 1, 0, 1, 0, 1. And the 0 state is the full 0 state, where we have all zeros everywhere. And we should not see anything else, especially on the data qubits. The data qubits should always be identical to one another, at least in the absence of noise. And here, what you see is that even in a noiseless setting, I'm still using AER simulator. I'm not introducing any kind of noise. I am getting results that I should never observe. What it means is that applying the T gate made us go completely out of our code space, and well, we've basically not applied a logical T gate. And so this is why we need to have a more complicated construction to apply logical gates. And this is what we call magic state factories. So again, unfortunately, because we don't have time to dive into this today, and also I'm not the right person to explain this, but the idea is that basically you need to have areas on the chip that are dedicated to generating what we call T states that will be used then together with quantum state teleportation to actually apply the T gates to the logical qubits. So you have your logical qubits here. So here, this is an architecture with four logical qubits of distance 5. So you have 1, 2, 3, and 4 logical qubits. And you have four magic state factories. And then you can use the connectivity on the chip with all these routing qubits that you have here in order to teleport the states that will be prepared on the magic state factories onto the logical qubits that you have here. So this is also, I hope you understand, sorry. I hope you understand this also why it is so complicated to build a fault-tolerant architecture, because you need this if you want to apply a universal set of gates to your logical qubits. And unfortunately, again, this cannot be simulated at the gate level. I mean, here you have something like, I think, 150 qubits on this diagram with only 4 logical qubits. This is not something that you can just put in an emulator and simulate. It's just going to crash. It's just too big. So we cannot show you that. But what we did is that we created logical qubit emulators that are going to abstract away this process and that are going to show you how to work with logical qubits once all of these operations are implemented and supported by the hardware. And for that, I want to show you 2 sample notebooks that we've designed and that you can retrieve online. And so I'm going to zoom a bit on this so you can see it better. Maybe just to show you how to retrieve them, you can go to felis.alice-bob.com/samples, and you have our repository of sample algorithms. And here we're looking at the algorithms section where you have these samples that are listed and that you can look at by yourself if you like. But yeah, just 2 samples that I would like to highlight, which is the first one where we work on Shor's algorithm. And so for Shor's algorithm, we're using the CRISP framework, which enables you to define the Shor's algorithm with only something like 10 lines of code. So in the notebook, you have the classical code that performs Shor's algorithm that we use for verification. And so you can run the classical algorithm. And then we have the CRISP algorithm that you can see here that implements the principle of Shor's algorithm. And that does also the post-processing of the results from the quantum circuit. And then you can run that, and you can run that on the CAD qubit emulator. On the logical qubit emulator. And what you can do with that is, well, first of all, verify that the results are correct, even in the presence of noise, because then you can, as I was showing earlier, when you are initializing the qubit, then you can play on the average number of photons, you can play on the quality of the CAD qubits and so on. And you can also play, in this case, on the distance of the code. And so you can, of course, check that the results are still going to be correct under your assumptions for noise. And you can also then perform a resource estimation, because basically what it does is that it's going to compile the actual circuit for the logical qubits, and especially for the gate state of logical qubits that we are supporting. And this is going to sometimes increase quite a lot the size of the circuit. And so you can check that. You can check the size of the circuit after compilation and see how it affects the size of your algorithm. And then finally, I want to show a last example where we play with the parameters of the CAD qubit, and we're doing this with something simpler than Shor's algorithm. We're doing this with a swap circuit, with a swap test, sorry, that is checking whether that is actually implementing a swap between 2 states that you have here, and by applying a measurement, we are able to produce figures like the one you can see below. I'm going to show you what this looks like. I'm going to zoom even further. You can see it well. Okay, I'm going to show the image in a new tab and then zoom on it, so that's going to be easier. Okay. Right. And here what you can see is the importance of different parameters. So you have the distance of the code, you have the number of photons, and you have the quality of the cat qubit. You can see here that when you were using a low number of photons, then basically the test is failing. This is the error rate that you're getting at the level of the circuit. So you can see that here no setting is working properly. And when we increase the number of photons, when we go to 7 photons, for example, then we can see here is a clear boundary. First of all, in terms of the quality of the qubit, you can see here that when we have the kappa 2 over kappa 1 ratio at 10 to the 3, you don't get anything useful, but at 10 to the 4, then it's starting to become interesting. And you can see also an interesting phenomena, which is that the quality is not always better as the distance increases. As you can see here, when we have a short distance that offers little protection against phase slips, we have a high error rate. Then it becomes better as the distance increases, and then it becomes worse again. And so what it means is that you've witnessed a regime in which here the dominant source of error was phase slips, and then as we increase the distance, then it becomes bit slips. And so you can explore, when you have a quantum circuit like that, you can explore how it performs under different assumptions on the quality of the qubit, on the distance of the error correction code that you're using, and on the number of photons that you have in your cat qubit, in order to find the best regime in which it would run. And then, of course, well, as you can see, we've done that for different numbers of photons. There's a number also of other things in this notebook where we, in particular, we're zooming on a transition to see exactly what it looks like. We're also studying the transition for different photon numbers with curves. You, we are also showing, a scatter plot of how the circuit succeeds versus the logical phase flip and bit flip error rates. So this is illustrating what I was showing earlier, if you remember, where if you are bad on one of the two dimensions, if you are bad on bit flips, then no matter how good you are on phase flips, then you're going to fail. And the reverse is also true. And then you can draw a zone with the logical error rates on the bit flip and the phase flip front, where your algorithm is going to work well. All right, so I hope that this gives you a good overview of what we're doing. I apologize, the presentation took longer than I hoped. But if you want to retrieve everything that we're doing, then you can go simply to our website, alice-bob.com, and then you have a cloud section where you can retrieve, so what I was showing earlier, so the link to the Google Cloud Marketplace, where you can test the boson 4 chip and access what I showed in my notebook earlier. Or you can simply go to Felis, which is an open source library based on Qiskit that enables you to run circuits locally without going through the cloud, and then you are able to use emulators and reproduce what I showed on the samples. When you are in the Qiskit provider, then you have links both to our documentation here and onto the sample notebooks that I showed. And so you just go to the page and you have these two links that enable you to go further. And if you want to contact us and if you want to learn more about what we do, we'll be happy to talk. And you can join our community on Slack, the Cat Tree, and where we are connected. We'll be happy to answer any questions that you have. But there is, I think, about 15 minutes left, and so we have time to take live questions from the people who are here.
Exactly. Thank you very much, Laurent, for the demo and for the presentation. And let's see if what would be the questions. Please write them in the chat or raise your hand and speak up. We are accepting both options. In the meantime, maybe, okay. Qiskit gets compiled to what? That's the first question coming out from.
Okay, so actually there are two execution pipes we have here. When you are using the local provider, when you are running circuits locally on emulators, then it's basically a Qiskit emulation engine to which we added a noise model and a target gate set. So Qiskit gets compiled to Qiskit in this case. We're all staying within the Qiskit ecosystem. But when we're executing remote circuits, like the one that I showed earlier, when we were running on the actual chip, then we are translating the Qiskit into QIR. And so our API technically takes QIR as an input, and then the QIR itself is translated into the language of the control electronics that we're using in quantum machines in this case.
Okay. And then the next question that's coming from a lot of interest to the presentation. Okay. 7-minute free of bit flip error is an incredible result,
Yeah.
first of all. What are your target audience for this tool? Yeah. And do you plan to create further learning materials for training courses also?
Okay. Yeah, so the target audience for these tools is principally students that are learning about quantum computing and want to understand how error correction works and what the final experiment is going to look like. So exactly what we are doing today. If you want to do research, then you will be more interested in the resource estimator tool, because here what I showed is only for circuits that can be emulated. And so, of course, then it puts a limit on the number of qubits that you can work with. And when we're working with actual emulation of short circuits, for example, we're quickly limited by the capacity of the emulator to reproduce the results. So if you want to study big circuits, then you will want to look at the resource estimator. But that would be a topic for another time. It would be a full presentation and by someone who is more qualified than me to talk about this. But you do have the link that I shared in the presentation, and then maybe I can also show it to you. Yes, this is right here. And so, yes, you have this resource estimator that you can use with bigger circuits that you would have designed in order to estimate how many physical qubits you would need. This is something that would be a good topic for another presentation, but that I would have to prepare. So I can't say much more about this right now, but I can encourage you to check it out and play with it and let us know what you think.
Thank you. You could also share the link in the chat if you feel like, so that
Yes.
people could
Yes.
go to it directly. There is a question whether the video will be available to rewatch. Yes, if you want it quickly, please email me. Otherwise, it will be uploaded to the YouTube playlist of the Quantum Flagship. I will.
Another thing so about the question about what is the audience for this kind of tools, I think that it also shows what we would like quantum computing to look like when we do have actual working logical qubits. It gives us a direction where we would like to go. Obviously, there is still a lot of work before we have a quantum computer that is able to work at the logical level because of the limitations that I showed earlier and the kind of architecture that needs to be built. But I think it's interesting to think about what the experience is going to look like eventually, and it gives us a direction for the developments that we'll want to make.
Maybe just to specify one more time education material. Was there already some implementation of this of Felix or use of Felix in some classes or courses in particular? Did you already have this trial?
We do give seminars to institutions that are interested. So we've already done a number of them, and then we can organize more, of course. Then feel free to contact me to organize this if this is something you're interested in. And in terms of educational material, we do have the sample notebooks that I showed earlier, and then there's also documentation pages coming together with Felis in order to explain all the things that you can do with it. So you can work with that on your own, and then if you want to do things together with us, then we're happy to explore collaboration opportunities.
Great. And you already have collaborations with some teaching institutions like universities?
Yes, not formal collaborations in that right now we're doing this more based on opportunities, so based on discussions that we have with various universities and where we get to present. So we did something last year at Yale, we did something at EPFL. I believe there was ETH also at some point. So yeah, number of universities that are interested in what we do and where we get the opportunity to present. And yeah, we're ready to do more of that.
Great. At this point, I see that all the questions have been answered, and for the time being, no other questions are coming.
Okay, great.
Let's give one more chance, last minute, and we could conclude with this.
Exactly. And so if you're interested in learning more, then I can recommend checking out all the things that I showed earlier. In the description, you've also got, sorry. In the documentation that we have here, you've also got a list of scientific papers. So if you want to read more about the architecture, about the physics of the cat qubits, if this is what you want to see, or on the full architecture to build a fault-tolerant quantum computer, you have useful links that are available here. And then, of course, if you're interested in learning more about a specific aspect, don't hesitate to contact us, and we can also put you in touch with more experienced people than I am, because I'm giving an overview, of course, but then we also have scientists that go deeper into some specific topics. So if you're interested in learning more about that, then feel free to reach out.
Very nice. Great. Thanks a lot, Laurent, and good
For
luck
having me.
with elaboration further of the Felix. And yeah, it's getting interesting when one needs to do a logical qubit out of a lot of physical qubits and want it full tolerant.
Yeah,
Good luck
exactly.
with all, and looking forward seeing your progress.
Thank you so much, and thank you for following us, and hopefully see you soon again.